So how does everybody feel about that derivative property we talked about on Fridays? Everybody okay with that? Derivative property good? You good? All right, so let's talk a little bit about the derivative property. So if you haven't figured it out by now, sort of the name of the game that we're like advancing towards is you can sort of think of like this line, and on the one side we can think about our signals in the time domain, and on the other side we can think about our signals in the frequency domain. All right, and kind of the name of the game that we're playing is sometimes we do things to our signals in the time domain, and we want to be able to think about what we've done to them in the frequency domain, and then vice versa. So for example, we learned that if we have a signal x of t, and then we take its derivative, then we've learned that what happens is in the frequency domain, then effectively you just multiply that Fourier transform by j omega, right? And conversely, if you integrate, that's equivalently dividing by j omega. Okay, we learned, for example, if you double x of t, you double x of omega. Okay, then we're going to learn some really interesting properties, right? We're going to learn what happens if you do stuff in the frequency domain, what happens in the time domain. So there's this whole concept of doing stuff in the time domain and figuring out what happens in the frequency domain and vice versa, right? And the reason we're doing that is that sometimes when you're doing signal processing, it makes all the sense to think about signals on the one side, and sometimes it makes sense to think about signals on the other side from a frequency perspective, all right? So today we're actually going to do an exercise where we start to think about signals from a frequency perspective, okay? And specifically we're going to start talking about filters. So I don't understand. It's not the marker, because this is the same marker I always use. It's the board. It's like they've treated it with something. Well, this is going to be an awesome lecture.
So it's like making an even to a function that is not even, shifting it on purpose.
Yep.
That would like help you analyze it.
Exactly, right. If you have a signal that's not even, you can make it even, analyze it using tools that you understand, and then apply the appropriate property to shift it back to where it was to start with. So today we're going to start with something that you've all, I'm going to apologize in advance. This is not going to,
Yeah, they cleaned it with the wrong.
They cleaned it with the wrong solution, it looks like. That's going to present a number of technical challenges for me. Okay, we're just going to make the best out of it that we can. So I apologize. So we've all seen, I mean, presumably everyone here has been to circuits too, and you've all seen this before, haven't you? Everybody seen that? What is that? RC circuit. And we learn what it does, like as a filter. Do we know what it does? Low pass. Okay. So I'm going to tell you something you already know. Okay. We know this is a low pass circuit. So what you learned in circuits 2, all right, and I know you learned this in circuits 2 because I'm currently teaching the same thing in circuits 2, all right, is you learn how to do the math that says, like circuits 2 is all about AC analysis, right? So you learn if I put in a cosine of some frequency, what happens to that cosine when it comes out, right? Circuits 2 is all about putting in a cosine and then making some prediction for what comes out. So, you know, what we're doing in this class really is not that different, right? Because we've learned that all signals are basically made up of cosines. So if you can do the cosine analysis on a circuit, you really know everything there is to know. All right? So we're going to try to do one end-to-end example today and kind of see how we feel about that. All right, so this is a resistor R. This is a capacitor C. Let's write and let's say this is our input voltage V in, and this is our output voltage V out. And I'm just going to write the differential equation for this circuit. This is something that I'm guessing everyone here should have seen about 6 times by now in various courses. But essentially what we say is that V in minus V out over R, that will give me the current through the resistor. The current through the resistor has to equal what? Current through the capacitor. And the equation for the current through the capacitor is? C dV out dt. Good. And typically the way you've seen this differential equation before is we're just going to reorganize terms. And we get it as dV out dt. Let's see if I can get this right on the first try. plus V out over RC equals V in over RC. Okay. So that's always a differential equation. So in circuits 1 and 2, basically what you learned was how to solve this differential equation for different kinds of inputs. Okay? And the approach that they typically teach you is, let's just start with certain kinds of inputs and solve the circuit for those special cases. Okay? And then hope maybe we can come up with something useful. But this differential equation is always true, regardless of what your input signal is, right? Your input signal could be a cosine, a step input, it could be a speech signal, a brain signal. Like whatever signal V in is, this differential equation will always correctly predict the output if you can solve it for V out. Right? That's the tricky part, solving it for V out. So, for example, you learned that if your input voltage is a step, okay, then your output voltage is what?
Exponential.
Exactly. You get one of these exponential jobbies where it goes like that. Okay? And you can get that answer, like you can actually derive the equation for that response by solving the differential equation. Okay? I'm not going to do it because you should know that by now. But that's how it works. And let's see. When you do this, what sets the speed of like how fast it rises? RC. Okay, so there's an RC time constant, and if you want it to rise faster, if you want it to climb faster, do you need a bigger time constant or a smaller time constant? Good. So smaller tau equals faster response. Okay? I have to use good handwriting because that's going to be on the board for like a day and a half now, right? Good. What do we? And then okay, so then you learn how to in circuits 2 you learn how to put in a cosine in for V in. So you learn that if you put in a cosine, what comes out? A cosine, right? If you put in a cosine at some frequency omega, the laws of the known universe tell you that what you're going to get out is a cosine. At the same frequency. No ifs, ands, or buts. Okay? And that's the only signal that has that property. If you put in a cosine at frequency omega, you get out a cosine at frequency omega. No ifs, ands, or buts. The only thing that can change is the amplitude of your cosine and the phase of your cosine. And there's equations for solving that. Okay, so we learned cosine in, cosine out. Okay, and that was all cool. So, now we're going to try to solve this in a more arbitrary sense. So, okay, we know how to work this for a step input. We know how to work this for a cosine input. Now let's work it for an arbitrary input. Because that's it, right? Once you got an arbitrary input, you're done. Right? That's it. I mean, there's nothing left to solve after that. So let's see if we can work this problem. So, I'm going to use my newly found understanding of the frequency domain to solve this circuit. Okay? So, what I would like to do is to take the Fourier transform of this equation. You with me? Okay, so here's what we're going to do. We're going to assume that the Fourier transform, so our output signal V out of t, we don't know what it is, right? That's what we wish to search for. But I'm going to assume that it has some Fourier transform V out of omega. Okay? Will you buy that? Will you believe me? Good. Will you also believe me that if I say my arbitrary input signal, I don't know what it is yet because I haven't defined it, but I am going to assume that it has some Fourier transform. Okay, so tell me, friends, let's start with an easy term. If this is V out of t divided by the constant RC, what do you think its Fourier transform is? Right, we've learned that if you scale a function in time, you scale it in frequency by the same scale factor by the same constant. Good. So this should be V out of omega over RC. Good. What about my input signal? What about this term? Oh, that's not a plus. That's an equals. What am I going to do with my input? Same thing. Good. So V in with respect to time becomes V in with respect to omega over RC. Okay. Now we've got the derivative of V out with respect to time. What am I going to do now? J omega. So watch this. J omega V out of omega. Now look what happened. Our derivative became just a linear function, which we can solve. So here's what I want to do. Let's solve for V out equals, shall we? What do you notice about these two terms? Factor out the V out. Okay. So V out with respect to omega. And then I'm going to factor out j omega plus 1 over RC equals V in of omega over RC. So far, so good? Have I lied? I don't think so. All right. Oh, I hate when they do this to the boards. That's ridiculous. I don't even know who to yell at. Like, I would. I just don't. I don't even know. Like, nobody tells you this stuff. For all I know, like pixies could come in at night and like clean the boards. I just seriously, I wouldn't even know who to call. Don't get me started on TU help, but that's a good idea. Okay. Oop, I lost my. Where did it go? My tail. Okay, so let's keep the conversation going. So I don't like that fraction. That's a little bit ugly. Let me just combine make like one fraction out of that. V out of omega times, what's that going to be? J omega RC plus 1 over RC equals V in of omega. Oh, look at that. Over RC. And finally, I get V out of omega. Yeah, the RC's cancel. How sweet is that? Equals 1 over j omega RC times j omega RC plus 1. Okay? Yes, sir?
Would it be useful to actually have on one side V out of omega over VI over omega and then everything else on the other side to get the transfer function?
Yes, we could do it that way as well. So the other way of writing this, so there's sort of like two ways of writing it. I've written it this way on purpose because I'm sort of trying to drive towards a bigger point. But no, you're absolutely right. So there's another way of writing the same thing, which is instead to write it as V out of omega divided by V in of omega. And we call that capital H omega, the transfer function. And in this case, that equals 1 over j omega RC plus 1. That's another way of writing this, and you should put that in your notes because we are going to do that pretty soon. We're going to start thinking about it like that. All right? Okay. So it seems to me like that's where the action's at. Okay? What does this transfer function look like? I mean, before everybody was pretty sure this was a low-pass filter. Does this say, where does this say low-pass filter in here? Okay. Well, which is my frequency term? Omega. So if omega is real small, what happens to my transfer function? If omega is real small, what's that term going to equal? Yeah. If omega is real small, then you can basically ignore the omega in comparison to the 1. Like if omega was 0.00001, you say, well, okay. we can basically just round it off, right? It's just insignificant compared to the 1. That leaves you with 1 over 1, which is 1. That would imply that for low frequencies, your output voltage equals 1 times your input voltage, or output equals input. So for low frequencies, signal's getting passed. Now, what happens when omega is real big? Right, when omega is real big, you can ignore the 1. Instead of ignoring the j omega RC, now you ignore the 1 because the omega is really big. So now you've got 1 over j omega RC. It's a fraction. It's a small number, right? If omega is really big, 1 over omega is really small. So in that case, for high frequencies, your output equals a small number times your input. So we can have some sort of confidence that what's happening is that high frequencies are getting passed and low frequencies are being rejected. Deal? Deal. Great. And basically, I'm trying to just write the bare minimum I have to on the board, and then I'm going to do the rest on the screen. I think I can get away with that today. I do need to, again, I know you've seen this before, but I feel the need to just put it on the board one more time. When we take a Fourier transform, right, with every other Fourier transform we've taken, we've argued that there's a magnitude and a phase, right? It's got to be a complex number. This is no different, okay? So this represents a subtle but important difference. So far, we've been taking the Fourier transform of signals, right? Now, you're looking at the Fourier transform of a system. You notice the difference? It's signal, system, signal. Okay, but they all work in the Fourier space, right? So you can multiply them, you can add them, like they play nice with each other. Okay? So we're taking the Fourier transform of a system. But it's just still a Fourier transform. You can take magnitude and phase. Okay? So just for kicks, just so we have it, just so we're all on the same page, if I wanted to find the magnitude of this expression, how would I do that? Right? If I wanted to take the magnitude of h of omega, how do we take the magnitude of a complex fraction? Break it in steps. If you've got a fraction, first step, magnitude of the numerator divided by magnitude of the denominator. That's always how you divide complex numbers. Right? Magnitude numerator divided by magnitude denominator. Okay, what's the magnitude of your numerator? 1. Now, what's the magnitude of your denominator? Yeah? Right, remember, it's always the square root of real part squared plus imaginary part squared. So if I were to write that, I've got my real part is 1, squared is just 1, plus my imaginary part is omega RC squared. Okay. And that's going to work out, that's exactly the way we think it's going to work out. Just like we said before, when omega is small, this fraction will come out to about 1. When omega is real big, this fraction will come out to be pretty small. And when omega is in between, this number will be in between. Okay, what about the phase angle of my transfer function? How's that going to work? How do I take the phase angle of a complex function? Almost. It's phase angle of numerator, phase angle of numerator minus phase angle of denominator. Okay. So it's always, so for example, if you had I don't know, k e to the j phi over m e to the j alpha. That's a complex number, right? So if I take that ratio, what's my final answer? It's k over m phi minus alpha. That's all I'm doing, right? That's all I'm doing. If I've got a complex thing, I take the magnitudes and divide. I take the phases and subtract. The only question is, what's my phases now, right? So what is the phase angle of my numerator? What's the phase angle of 1? 0. Right, 1 is e to the j 0, right? If you remember your complex numbers, real, imaginary, here's 1. Phase angle, 0. So phase angle of numerator is 0 minus. Now what's my phase angle of j omega RC plus 1? Yep. And again, I'm doing exactly the same thing. Let me plot here. Here's 1. Here's omega RC. So here's my complex number. And I want to know that phase angle. Well, that phase angle, by definition, is the arctangent of imaginary part, omega RC, over the real part, which is 1. All right. So at low frequencies, I've got minus inverse tangent of 0, which is, what does this do for low frequencies? If omega is 0, which is the lowest frequency, I've got 0 minus inverse tangent of 0. That's almost a tangent. Now I can't even erase that. Oh, the shame. The shame. It's okay, I'm tenured. They can't fire me now. Okay, so this is theta, and this is tan theta. So what value of theta gives me tan theta equals 0? 0. Good. So for low frequencies, theta equals 0. For high frequencies, so if omega is infinity, which is about the highest frequency you can get, you've got minus inverse tangent of infinity. So what value of theta gives me a tangent of infinity? That's pi over 2, and it's minus that, so minus pi over 2. Okay. Are we good? All right, let's put this into action. I'm done writing. I think the board has given up. Or rather, I'm giving up on the board. So give me a minute here to change gears. Maybe the projector will work today. You should at least get one or the other, right? You should either get the board or the projector. Otherwise, I can't do my job. All right. It's Monday. If I turn off the lights, are you all going to sleep? Maybe. Let's find out. Oh. Everybody done with the homework? The computer assignment. No. Well, you've got till like 2 more days. That's like a lot of time. All right. Sort of. Okay.
So like those two frequencies, right, when they're multiplied, like functions multiplied or just
yeah, I don't know. Somebody else asked me the same question. I'm not
determined if you had in my board I said you had to add them because when I compared the time plots, that was the only way I could get the time plots in that.
The time plots certainly look like they add, but the frequency plots sort of hint that they multiply. And I don't really know what to make of that. I mean, they would look. Yeah. Well, I think I know what's happening, but I don't want to say because I want you to think about it. But discuss. We'll talk about it later. Okay. So, okay. Let's do this. Clear figure. Shall we make a filter? Great. Okay. I need a value of R and C. In fact, I don't even need separate values of R and C. You can just mush them together in one variable. So how about we say a millisecond for RC? Is good? Glad you agree. All right. So let's do this. Let us take a square wave, a rectangular pulse rather, and filter it. Okay? So, first let's build our, why don't we start by building our filter? Should we do that? Okay. So H equals, let's see, how am I going to do this? You guys want to see some, this is some MATLAB nonsense right here. 1 divided by j omega RC plus 1. Is it going to let me do that? It did. All right. This is some highly non-conventional MATLAB. I don't really expect anyone to know this, but it's just cool that you can do this. So what I've done here on the line that's highlighted is I've defined a function. Okay? So this is an inline function. So h is a function that takes as input some variable that it's going to call omega, and whatever value of omega, it's going to return 1 over j omega RC plus 1.
Is that the at symbol?
That is the at symbol. That's how MATLAB knows to make it an inline function. And if you look, I came down here and said whose. It says, what is h? It's a function handle. So now I can come and say things like, oh, what is h of, I don't know, 1,000 radians per second? It's that number. Yeah. All right, what is h of 2,000 radians per second? It gives me an answer. Or I can say, what is h of, and then I can give it a whole bunch of values, right? I can say, what is h of Lin space? I don't know, 0 to 5,000 radians per second. But I'm not crazy. Let's only have it give me 10 values. Okay, it gives me the 10 values. The point is, it's just a tool. Yes, sir?
What's like the MATLAB term for that, in case I wanted to dock it?
It is, what is the term? It's an inline function, I think. Let's see. Look for inline. Look for inline. Yeah, you can also do it with the inline function. Okay. All right. So, somebody used my laptop over the weekend and had dirty fingers. I think that's pancake batter. I'm serious. I don't know if that indicates my wife or my kids, but either way, let's talk to someone about that. Okay.
Maybe you'll find somebody on like the board.
Right. Okay. So let's go ahead and look at the transfer function of this thing. So I need a frequency vector. So omega equals let's see, Lin space. Let's live. Okay, 0 to 10,000 radians per second, and let's get a whole bunch of points here. Let's have it give me 10,000 points, and now I can say plot omega, comma, absolute value of h of omega. Okay, so is everybody okay with what I've done? I defined omega, and then I said, please plot for me h of omega, but h of omega is complex. I just want you to please plot for me the magnitude. Okay? So, what's on my x-axis? Frequency in terms of radians per second. And what's on my y-axis? Yeah, we're going to call it gain, although you could call it amplitude if you want. Okay? And boy, that text is pretty small. Don't try this at home. Literally, like, it won't work. Big text is a function I wrote that just automatically makes everything bigger and easier to read. But you don't have it because I wrote it. I can give it to you, but I'm just saying you don't have it. Okay, so is this a low-pass filter? Yeah. If I put in a low-frequency signal, remember what our formula said was output equals this function times input. You with me? So if I put in a cosine at frequency 1 radians per second, what comes out? I get out a cosine at 1 radians per second, and the amplitude of my cosine is multiplied by 1. That's a low-pass filter. Output equals input. What happens if I put in a cosine at 10,000 radians per second? I'm still going to get out a cosine at 10,000 radians per second, but its amplitude, if the amplitude going in was 1, the amplitude coming out is 1 times 0.1. So that cosine will come out a tenth as big as it went in. That, my friends, is a low-pass filter. Low frequencies passed, high frequencies hit the bricks. Okay, let's add the square pulse in, shall we? All right. So let me, I'm going to give this its own, we're going to need a few subplots here. So let me just do the same thing. Let me go ahead and stick it in the middle there. All right. All right, so now we need to create the, I want to get the Fourier transform of the square pulse. Just use the sinc function. So I'm going to say something snappy like, hold on a second, help sinc. There's a trick to using the sinc function. Sinc, it's sine of pi x over pi a. Okay. So it's sine of a omega over a omega. Okay, so let's say a equals 1. So for our square pulse, we would know that x should be, x of omega should be sine of, it's sine of a omega over a omega. And I can, so let's just say that. Okay, so sine of a omega divided by a omega. There is a way to do this with the sinc function, but I'm going to just hold off for now. Does that work? And I can plot that. So subplot 311, plot omega, comma, absolute value of x. Whoa! What am I looking at? Yeah, the frequencies are kind of a little bit mismatched. Okay, so it looks like so if your cosine, sorry, if my square pulse has a width of 1 second, right, which a equals 1, that means it's a pretty broad signal. If it's broad in time, it's narrow in frequency. So where would my first zero crossing be for my sinc function? We said it was pi over a. So my first zero crossing is at pi over a, which is pi radians per second, like 3 radians per second. And look at me. I've got like 1,000 and 2,000. So yeah, like all the action on the sinc pulse is happening at like 3 and 6 and 9 radians per second. And over here I'm talking about thousands of radians per second. So why don't I make my sinc pulse, why don't I make my rectangular pulse skinnier? Okay, that should solve the problem. There we go. That's a little too wide. Let's make it, let's pick something right in the middle. Okay, that works. All right, so all I did is I made my square pulse skinnier, and by definition that made its Fourier transform broader. Okay. So what am I going to do with those two functions? Remember, my whole goal is to get the output for an arbitrary input. So there's the Fourier transform of my arbitrary input. There's the transfer function in the middle. So what does the formula say I'm going to do to those now?
X times, where is it, H?
The formula tells me specifically that the output Fourier transform equals the input Fourier transform times the transfer function. That's what it told me. Output Fourier transform equaled input Fourier transform times transfer function. Isn't that right? I mean, we derived it. It's part of that jibber jabber that I can't erase now, and that the next class is going to have to look at. Okay, so should we multiply these together and see what they look like? Because it seems like that's the right thing to do. So I guess I'm going to do that, and I'll plot that in the third window at the bottom. So subplot 313, plot W, comma, absolute value of h of omega times x. And hopefully this works. Hey, look at that, first try. So all I did with my plot function is I said, take h of omega, take x, multiply them. So in other words, what I'm saying is take the value of h at omega equals 0, times it by the value of x at omega equals 0. Take the value of x at omega equals 1, multiply it by the value of h at omega equals 1. Wash, rinse, repeat for all frequencies. So what do you notice about our output? So what you're looking at the bottom should be the Fourier transform of the output of our function. What's that? No, ask the question.
Multiply together?
No, we took the input times, we took the top plot, which is the input, times the middle plot, which is the transfer function. We multiplied them and we got the third plot, which therefore should be the Fourier transform of the output. Let me put a legend on here.
Oh, so V out, right?
Exactly. So this is V in. This is the transfer function. And this is V out equals transfer function times V in. Does that make sense? All I'm doing is I'm just plotting what we derived on the board, right? We started with a differential equation. We took its Fourier transform. We solved it. So the Fourier transform of the differential equation told us that the output voltage is equal to the the output Fourier transform is equal to the input Fourier transform times the transfer function. So what this implies is, if I took the inverse Fourier transform of that top plot, what would I get? You'd get your square pulse back. If I took the inverse Fourier transform, which we haven't talked about how to do, but if I were to take the inverse Fourier transform of my top plot, I would get my square wave back. If I took the inverse Fourier transform of my bottom function, what would I get? I'd get my output voltage. That's the whole thing I'm trying to get, right? The whole point of this exercise is I need a method for getting the output when my input is some arbitrary function. And what I'm telling you is we have a method now. Okay? Instead of taking a time domain approach, a time domain approach would basically be solve the differential equation. Okay? What I'm offering you is an alternative. We're going to get our answer in the frequency domain. So the steps are as follows. Step 1, take the Fourier transform of your input signal. And we know how to do that, right? Now that we have the FFT function that we know how to use in MATLAB, we can take any signal and get its frequency content. Right? Any signal. You did that in your homework assignment, right? You took the phone tones that I gave you and took its Fourier transform. Take the Fourier transform of the input, multiply it by the Fourier transform of the filter. That gives you the Fourier transform of your output signal. All right? If there was a method for taking the inverse Fourier transform of your output, what you'd be left with is in fact your signal, the output that we wish to seek. Okay? And it turns out there is such a technique for taking inverse Fourier transforms. It's basically the same way that there's an FFT function, there's an inverse FFT function that just runs the FFT backwards. Okay, so you stick that in, you take the inverse FFT, out comes your signal. It's pretty sweet.
Would that be an exponential in this case?
What would it look like in this case?
Since it's just an RC circuit with a square wave input.
Yes.
You have a rise and then a fall exponential.
Absolutely. So let's see, we've got a few minutes left. We can plot this. I'm going to show you another MATLAB trick that you haven't probably seen before. And I'm going to mess with I'm sorry, I know this is like totally, there's 2 columns. Sorry, let me just think for a second. That's going to be 4, I want that to be 6 and 2. Survey says, oops. Okay, so I just took all those same plots, popped them over on the right. All right, just by changing the subplot. So now I've got, for example, my first plot. I said take subplot. I want 3 rows and 2 columns. So there's 1 row, 2 rows, 3 rows. First column, which is currently blank, and here's my second column. And I'm saying I want my first plot to occupy axis number 2. So it goes 1, 2, 3, 4, 5, 6. That's how I did it. Okay. So let's go ahead and make, let's go ahead and plot in the left-hand column. Let's do the time domain analysis. All right? So this is actually pretty easy. So let's see. Oh, we need a time vector first of all, huh? So let's see. T equals ln space minus, I don't know, 20 milliseconds to 20 milliseconds. And I guess we'll take 10 to the 4th points as well. So let's see. X equals, so you've seen this before, x equals 0 times t. X of absolute value of t less than a equals 1 over 2 times a. And now we can plot. So subplot 3, 2, 1. Plot t comma x. Survey says, hey, look at me, I got it on the first try. Okay? So all I've done is, I've created for myself a square pulse whose width is a, and it goes from minus a to a, and whose height is 1 over 2a. And there he is right there. Okay, does that look good? All right. So if you take the Fourier transform of this signal, you get that signal. Okay, so then you take that Fourier transform times this transfer function, we get this. We needed a method to take the inverse Fourier transform. What I'm going to do, instead of taking the inverse Fourier transform, I'm going to use a slightly different tool, but it's a little bit more accurate to give you the final answer. So we're going to say, let's see, h equals transfer function of 1 comma RC1. I'll explain where this comes from in a minute. Don't stress over the fact that you don't get where this came from.
Are you going to post this out?
Yeah. I'll post it. Yes. I don't expect anyone to type this fast. 3, 2, 5. Rats. Let's see. Y equals LSIM. You think I remember how to use the LSIM function? HH comma X comma T. Plot T comma Y. Okay, now before you start applauding, which I know is your natural response at a time like this, so I just want to discuss if this makes sense. So we talked before about how if you put a step input, you get a rising charge, and that's exactly what we're seeing here, right? And then when you take the square pulse away, you've got a decaying discharge. Is that right? Good, and that's what we're seeing. So I just want to do one thing now to kind of make my point. So minus 20 e minus 3, 20 e minus 3, 0 to, I don't know, 105. And I'm going to put that in here. I just want to hold these, I'm just trying to hold my axes constant because I'm going to start changing a variable now. All right, so here's the big reveal now. So my question for you is, what happens when I change RC? You told me that if I made RC smaller, that my rise time would be faster. Shall we see? So you said if I make RC smaller, rise time gets faster. So I'm going to make my rise time, I'm going to make my RC 1/10 of what it was a moment ago. So let's see what happens. You've got 5 graphs to look at the same time. What just happened? So what stayed the same? 2 things stayed the same. Right, the 2 top plots stayed the same because I didn't change my input function. Did I? No. Okay, middle plot. Actually, no, screw the middle plot. Let's look at this bottom plot. Did my rise time get faster?
Yes.
No question. Rise time got faster. Now, what happened to my low-pass filter? Did I increase my cutoff frequency or decrease my cutoff frequency? I increased my cutoff frequency. Whereas a moment ago, I was really only passing signals up to like 1,000, maybe 2,000-ish radians per second. When I made RC smaller, I made my cutoff frequency bigger, right? This is now passing, it's still a low-pass filter, but it's passing more low frequencies than it was. When it passed more low frequencies, what happened to my output transfer function, to my output Fourier transform?
Closer to the input.
It's closer to the input, right? Because remember, output equals input times transfer function. So by opening up my transfer function more, I'm passing more high frequencies. When I pass more high frequencies, what's going to happen to my step response? It's going to rise faster. Why? Because I passed more high frequencies. That's how you get your corners. We learned where do you get your corners from? High frequencies. Want to get your corners? No problem. Open up your low pass filter. Pass more high frequencies. It's still a low pass filter, but you're passing more high frequencies, and by passing those high frequencies, you get the nice little bits that you need to create your edges. Yes?
How come the previous graph for gain, this one looks like it has the 20 dB per decade slope?
It's only because it rescaled the y-axis. Before it was from 0 to 1, now it's from 0.7 to 1. You just zoomed in on a little piece of it. If I wanted to do a little bit of a fair, make it a fair fight, what I should have done is set that, force it to hold the same axis. So 0 to 10, let's see, 0 to 1. Yeah. So if I do it like that, you see it's a lot more open. And if I rerun it with the old value now, basically all it's doing is that it opened this up so much that you were only seeing from here to here. So it just looks like it's the 20 dB, but it's really not. Okay, that was kind of fun. I'll put this code online, as soon as I find internet.
How come we're not seeing a constant 20 dB?
Because you need to make, in order to see the 20 dB per decade, your x-axis has to be logarithmic and your y-axis has to be in decibels, which I'm doing neither of.